All right, so good morning, everyone. So basically today, the idea is to run some live demo simulations, simple simulations. I will solve different features with 2D, 3D simulation software packages from Ansys portfolio. So this is mostly focusing on high frequency simulations. I hopefully we have time to also look a little bit those low frequency cases. Basically, I will mostly use today two different software packages. Ansys Electronic Desktop, which is able to do different simulations inside. And the second different software is Ansys SI Wave, which is a circuit board simulation tool. And basically, you should have free access on all these software packages from the Ansys customer portal. There's a student version. There's some specific limitations with the size of the design, if I understood. But basically, all the functionalities, features are included. And I strongly recommend to try it and play with that. So that's the best way to learn to use. And in order to find some simple, good ideas how to use the software, just go to YouTube and Google or use YouTube search to look for Ansys simulation demo or something like that. So you can find plenty of nice videos with step-by-step instructions how to do something. And today I'm just hoping to willing to solve you how to open the software, what settings to do in order to make it easy to run some basic simulations, and giving you the first steps and features you can find with this software packages. So it's a pretty big package. It's something a few gigabytes to download, and but it's pretty straightforward. It just asks where to install, and please use the default installation directories and so on. So it's just making it easy. And basically, as soon as you have installed the package, you can find from your hard disk a new folder which is named like shown on my screen, Ansys EM Suite 2020 R2. So this is the software package you will get. And under that, you can find the software I'm using today, which is the Ansys Electronic Desktop. This is kind of the user interface. There's some additional tools, and today I'm opening a second software, actually the two green ones, Electronic Desktop and SI Wave. But let's say that this Electronic Desktop is the key software I'm using today, and I will explain later what's inside. Basically, the other tools here are more focused tools for some specific simulations. Maybe something interesting to point out is this Twin Builder, which is similar to Simulink from Siemens portfolio. So it's a multi-physics system level simulation. So you can combine hydraulic, mechanics, electronics, temperature simulations, piping, airflow inside of that. So it's a system level. So basically you can build up a digital model of electric motor or combustion engine, fossil engine, or wind turbine, or whatever. So basically you can really build complex systems with that. So anyway, if you open this software, you will see this kind of screen. So basically, actually, most likely you will see it at this kind of screen. So this is kind of the user interface. So on the left top corner, we have the project manager where we can open different projects. Then we have properties window and then the empty area. I'm clicking on the right lower corner to open 2 additional windows, which is just nice to have visible. So this is the progress. If you are running simulations, you can see what's ongoing. And on the left side, there's a kind of message folder. You can see different warnings, or if there's errors in your simulation setup, this is the place you can see. And all these windows are something you can move around, and just used to have it in this order. Cleaning up the windows. So basically, when starting up something new, in order to do something, so it's more or less empty. So the first thing is to go to upper menu, and we need to add a project. And from the project, you can add different simulations. So this is a user interface, which is common for many different simulations. And under that, you can open the kind of more specific simulation packages. Today, we are mostly using this HFSS design, the first one. That's the high frequency 3D environment. This is actually a circuit board simulator under this electronic desktop 3D layout. Then we have Q3D, which is the RLC extractor, 2D simplified simulation setup. And this is the SPICE circuit design. It's actually a SPICE environment, like ADS or LT SPICE or something like that. Then we have low frequency simulations, Maxwell, and 2D version of that, rotating system, and we can do the digital twin here too. And IcePack is the cooling simulation, and we can also do some mechanics simulations. We are not speaking today, but basically these are the options. If you have nothing visible here, then we have to go to the settings. So all the settings can be found under the tools and options and generic options. So if you are not able to see any projects by default, you have to go here, and it opens immediately and set target configuration. You might have here something which is kind of just saying that SI or RF, so you can't see all the designs. So just have all, and that's it. Basically, you will get all the projects visible. There's much more properties, but typically you don't have to touch these options too much, except if you want to change some like default units. If you are willing to play with millimeters, you can specify millimeters here. If you are playing with small devices, it's easier to use millimeters than meters. If you are playing with factory tubing system, which is hundreds of meters or something, meter is more convenient, and then so on. Same, the directories, just be sure that you never use web cloud for the temporary files or project files. It will slow down your simulations a lot. So always use the local computer where the software is installed. That will speed up simulations a lot. So, and of course, you can have user interfaces, libraries somewhere where you have access. For example, for many times you have limitations where you can save data with computers. So you have to specify a library or folder where you can save files. That's just typical Windows stuff. So basically, from the tools options, you can find all the settings. There's actually the next one, HPC. HPC means high performance computing. That is the place you can allocate computer resources for your simulations. So you can choose which simulation you are doing, and then from the edit button, you can see how many CPU cores you can use, and just keep it 4. This is the default. You don't get any errors of non-existing. So you can always use 4 cores for any simulation because that's coming with the software. So you don't have any error messages that you are lacking of licenses for extra computing. I think so the default is 4, but because I'm using my laptop with more CPU cores, I'm using 8, and use as much memory as possible. That's always required. My laptop has 32 gigabytes, and it's already not a lot for simulations. So many simulation software packages require a lot of memory. Heavy simulations kind of require 2 terabytes. And typically in that case, we are using cloud system for that. So small simulations up to 500 gigabytes, we can do in a workstation. More heavy simulations, we have to go to cloud. Simple demos can be done with 16 gigabytes. A bit more complex demos or simulations can be run with 32, but any heavier design, you really need 128 gigabytes or more to run the simulations. That's just the life of computing nowadays. But basically, this is the initial settings. That we can go to project and open a new window. I'm just cascading my windows so that I can see multiple windows at the same time. So that will open us an area where we can draw something and bring CAD files. So basically, we had 2 options to start up. So this is my project, which is now open, and you can see different steps. And the basic idea is that we are going from top to down, step by step. And these are the steps required to do the simulation. We can bring in 3D components, which are like Murata is maybe, or Renesas is doing a 3D component of antenna. So you can add a 3D component from the library, but we don't have it today. Let's do it simple way. So typically in real life, in industry, you bring the CAD from file. So you are importing a CAD file, and it's basically any drawing you will get from SolidWorks or Parasolix or CATIA. CATIA and SolidWorks are the de facto tools industry is using nowadays. So if you go to work to Volvo, Ericsson, Saab, whatever, Grundfos, big companies, somebody will draw the drawings with CATIA or SolidWorks. The other software are really rare nowadays in the industry. And step files are de facto standard to share files between software. So point step file is just a CAD geometry file you can kind of drop in. But now let's keep it simple. I just do something simple today. So how to start something? So I go to draw menu here, and this is my drawing tools. There's a huge number of different drawing tools and features you can do, but let's keep it simple. I choose the box here, or let's say I will take a seat, 2D seat. So I'm drawing a box, which is 0 dimension, so it's flat. There's no Z dimension, so it's just a kind of flat piece of infinity thin sheet. And by default, if I click it active, I can see the properties here in the window. And it has, because it's no thickness, so it's not really a material. It's nothing. It's just a sheet. So I can default kind of give a definition for that. But let's go step by step. So I can also, now we can see all the objects here under the properties menu, and I can design the size. Okay, I have meters now, so I will change it to 0.2 meters times 0.2 meters, and just minus 0.1 minus 0.1.0. So I should actually use millimeters here, but I just shrink it to 20 centimeters times 20 centimeters, small sheet. I can also take off the grid, but I will keep the grid on. So now let's do a simple monopole antenna and see how to simulate a simple antenna system. So I will take the cylinder tool, drawing tool. It will snap on the middle. So you can see it will snap on the middle edges automatically. It's easy to find the point. So I'm working on this layer now. this is my main coordinate, global coordinate system. So I will click on that. I say that I will just draw any size. So this is my cylinder. So I was not giving any specific dimension because I can now edit the dimension from here. So I will say that it's something like it's 2 millimeter. Oh, sorry, the heightness. It's this is meters, 0.1 meter, and it's now too thick. So I will change it to 1 millimeter thick. So it's a small cylinder here, like an antenna. I will change the colors to something different to see it. Now it's touching this bottom plate. So I was starting to draw it, but in order to kind of do an excitation for my antenna. So this is my monopole antenna, 10 centimeters long, but I need to have a small gap between the, let's say this is my ground. This is my ground layer, and this is my antenna rod. So I need to have a small space here in order to make a kind of signal generator or excitation for that. So I will move up this cylinder a little bit. So you can see that its center position is 0.000 millimeters or meters. So I will increase it 1 millimeter up like this. I was adding 1 millimeter to the coordinates or origin of the coordinate. Now I have a small open space between that. And there's many ways to do excitations in these simulations. Basically, we have two kind of ports, lump ports and wave ports. So what I'm doing now, I'm going actually on this model step. So I'm adding my CAD model drawing to this setup. So now I will go and add a lump port. And how to do that? It can be inside of your simulation, middle of your simulation. So I need to have a kind of voltage difference or signal between this ground and the antenna. So I will add a small rectangle. See, actually, I will make this a little bit transparent. So I activate that, click here, and make it more transparent so I can see it through my cylinder. Now I will go to this tool. I will take the grid system away. I will move my mouse so that I can find a snap point here. Now it's drawing a rectangle in this XY set. I will change my plane to YZ. Or let's take XZ plane like this. I will zoom out and I will just find a snap point here. Okay, this is my way to draw a rectangular seed like this, but it's too long now. It's going to the side, but that's okay because I know that I can edit this this length of that component. Oops, not that one. It's, where's my rectangle? Oh, here we are. So it's too long. I will edit that like this. So I string the size. Oh, okay. I can do it 2 millimeters wide because my radius is. So this is my rectangular seat here under the cylinder. So it's kind of going from the antenna element to ground. So basically, I will use this seat, just kind of a guideline to define my port, lump port. So I don't give any material for that. No, so now I have two seats with 0 thickness and my 10 centimeter, 2 millimeter diameter antenna. And you can see that its material is vacuum. So I can, typically you can do always many things in several ways. You can right click something, or you can go to here and edit the properties. So I will now just click and right click and assign material. This will access material library. and there's plenty of materials with electrical properties inside. So, and you can search something. So if we would like to use the copper, I will just choose this copper material, and you can see permittivity is 0, permeability more or less 0, and it's not ideal conductor. So there's slightly, so the wavelength is different than in vacuum. So it's not ideal conductor. I'm using copper here. So now you can see it's copper, and we can also see on this material library that one material is now under the copper selection. My ground plane is, there's no definition yet, so there's nothing in that. So I need to define what's my ground. So I will activate that. And now, because this is 2D seed, it's not a 3D component. I'm not able to define a material for 2D non-thickness material, but I can add a boundary. So boundary is kind of a simplified expression of property. And in this case, it's electrical property and about the conductivity or absorption properties. So you can see there's lots of different boundary conditions. And we can specify different ways that. So perfect E means that the E fields are perpendicular to the surface, like a 90 degrees angle coming towards the ground. So the ideal ground, I could use the perfect E. So if I click that, and I can say infinity ground side, it means that my ground is huge layer with this ideal conductor. But because this, let's do it in more realistic way. So that would already work for me, but I will use a different boundary condition. I will use infinity conductivity. So this means that I can specify my ground planes. Let's say that it's steel. So I will select the stainless steel. You can see it's less conductive. So steel is not really good conductor. It's about almost 5 times weaker than copper. That's why all the electric wires are copper. It's good conductor, but let's just use steel here. When you go to really high frequencies, like 5G mobile phone, you really have to think about, because the electromagnetic waves travel on the surface. No, actually, it's a huge effect what kind of surface you have with the copper. But when we are playing with low frequency, let's say 1 gigahertz or 2 gigahertz, you don't have to use the surface model for that. It's only in higher frequencies. So actually, more realistic, in tens of gigahertz, you need to think about what kind of polishment you have or flatness you have with the copper. Otherwise, you don't really care of that. Now, I can also say here, infinity ground side, I'm using steel. Okay, now I have, as you can see, it's not written here. Oh, sorry, it's here, infinity conductivity, but we also got something here under the boundary. So you can see that it's now here. The other way to do it is activate this, go to boundaries and assign. And now we can find the same menu as I can find by right click here and boundary and kind of conductivity for the surface. So these are the 2 main ways to give material property, which is electrical conductivity or limited conductivity or and so on. So boundary is always for the surface or sheet. So it's, and for 3D material, you can use both. You can use volume conductivity and surface conductivity. It can be also different because many times different materials are coated, like aluminium. You can have oxidation on the surface of the aluminium. So it's a good insulator in that case, with low voltages. With high voltages, the oxidation on top of aluminium will actually break through, and you have almost full aluminium conductivity. So basically now I have specified my two CAD objects. Oh, actually, there's a three because I have this small seed as a third one. And now I need to define, if I go down these excitations, boundaries, I need to also say what's around the antenna. So I know that I have a huge ground plane here, which is infinity size. So it's never ending. So it's kind of ideal, huge ground plane. But what about the air here around? Now we have to think about how simulations are behaving. So if I need to measure how this antenna radiates, I should capture all the electromagnetic waves which are kind of transmitted, radiated away. And I need to measure that. And how to measure that, I can do it with a boundary condition, once again. And typically, you need to define the boundary condition around your system, except if it's a coaxial cable, which is kind of all the electromagnetic waves or travel inside, or kind of a transmission line. But I go to Up menu, Solution Setup, and here we can see that I'm now having terminal. There's different solvers. You can use model solver. If you remember the Wednesday, I was speaking about different solvers. So the model, terminal. Model is using power. Terminal is using voltage. We can also do time domain transient simulations or self-resonance simulations with eigenmode and characteristics mode. And this is the shooting, bouncing ray tracing system here. Easy way to do the boundary condition is to click here, outer region. And now I'm specifying a radiation boundary to my setup. And that's typically good to start with. These are more accurate. Oh, sorry, this is more accurate, but it's more heavy to simulate. So I'm using a simple radiation. And this is a hybrid where you can specify surface currents. So this is one way, easy way to define the boundary condition. So just go to HFSS, solution setup, and outer, and that's it. But I will show actually how to do it manually, which is the same way, same result, but what it means in real life. So I select the box tool. I click on the corner. I draw a box like this. So now I have a cubic, which is vacuum. It's okay. We are, and I say that just display wireframe. So it's just now it's just using the lines on the edges, so we can see through. And I can also say that make it transparent. So if I click activate that, we can see through. So I can use this as my boundary condition. The outer region will do the same, but I will now select that. And what's the size of my box? It's a little bit too small, maybe. So I will make it a bit wider. 0.4. The basic idea is lambda per 4. So the wavelength divided by 4 is at least the good distance from the highly radiative antenna to the side. So I just want to make this a little bit larger than. Oh, sorry, not that one. I was planning to increase the height of the box like this. Now I have surely big enough box around my. I will also decrease the size of my coordinate system, so it's not hiding my antenna. So this is my design setting now. So I have now a box around my antenna, but I have no definition for that. So once again, I can go here, right click, boundary, and I say radiation. So you can see that this radiation is exactly the same that was proposed by the outer open region. Now it's radiation boundary. So basically this boundary is now the same as in EMC chamber or in antenna lab. You can see those triangles absorbers on a wall. So this is my absorber. it will kind of eat all the electromagnetic waves which are radiated by the antenna, and nothing comes out this box. So this is kind of blocking the radio signal and measuring at the same time, kind of measuring the how much energy comes in which direction. So this is my boundary conditions. I have the solid ground, and as you can see, it's actually my drawing is so that the radiation boundary. There's no reason to draw this box under here because nothing travels inside below the antenna because this is infinity good ground. Nothing goes through the ground layer more or less. Well, actually, a little bit yes goes because this is steel, so the steel is not ideal, but it's marginal. So I don't care how much radiation I will go down under the ground. In this case, I am interested in how much this radiates. So this is my boundary conditions. That's a must. You need to have a boundary condition around all the size of your antenna. Otherwise, you don't get a realistic. You will get results, but you will get warnings and you will get false results. So radiation boundary. The easy way was to go solution setup here and outer open reach. That's doing the same. Okay, now we have more or less all the. Oh, okay. I need to save this time to time. In the live demo, everything will crash time to time. So simple monopole. That's my antenna name. Saving the file. And while it's waiting, as I was saying, the demo has always something wrong. Let's see what happens. Oh, do I have licenses? I was not checking out because we are using. I'm using VPN, so it might be so that the VPN is not active at this point. Okay, it's connected. Great. So everything's okay. So most likely the VPN was slowing down something. Okay. Now we are here at this boundary. Now I need to do the excitations. I will click this box and I can make it invisible from this menu, but I will press the Ctrl-H button here to hide it. I can get everything visible from this eye picture here. I can click this and click hide button here to make it to hide it. So this is my excitation point, but we haven't defined yet the excitation. We can do it in that way that I will click on this sheet, and from that click assign an excitation. The same way I can do it by right-clicking here and go to assign excitation here. And this is the default lump port. Lump port is the most commonly used excitation to apply. We can also do wave ports for the waveguides, transmission lines. We can also have a plane wave coming from the, like, if the radio signal is coming from really far away, like tens of meters or kilometers or thousands of kilometers, or from the space, it's a plane wave, more or less. So once again, you have to think about the aperture of your radio source. If it's really far away, it's a tiny source, and the wave is closely a plane wave. You can also link far field, near field data, and there's plenty of options, but just do it simple, lump port. Now it's asking, why is my ground? And when I click here, it will. So I'm not willing to use this my antenna as a ground, but I would like to use this the ground plane, the steel plate, as my reference. So I will click OK. That's it. Now I have excitation, and we can see that this is my excitation port. So the voltage comes from here up here, and that's it. Simple excitation, easy way to do the excitation. So that means that this is my reference, this is my kind of antenna element here. And this is the way how where the power or voltage in this case will come inside. So now what's still missing is, as a next step, we don't have hybrid regions. We will step over that. As I was said on Wednesday, meshing is more or less automated. So we can do some manual meshing here, but I'm skipping that because I will just use the automation. So the next step is from top down, we are now going to analyze it. So we need to say what frequency this antenna is going to work. So right click, add solution setup. We can do it a simple way, auto, but you will just say, this is my lower frequency, this is higher frequency, and everything comes automatically. But for learning purposes, I will use the advanced. So it will open a window with lots of options, but basically there's only few things you need to edit as a starting point, from the starting point of view. Let's say that this antenna is going to work in a single frequency. I don't know actually the resonance frequency. This is just, I just draw 10 centimeters long, but I would guess that, let's try to get it around 2 gigahertz radiation. And then this is saying how many iterations we are doing in order to increase the meshing. So the maximum is 6. I will say that you can do 9 iterations, and this is how much error for the meshing we let it be. I will keep just the default to 2% here, and that's it. That's the only thing you need to specify here. You can also say that you are doing a multi-frequency simulation for the antenna if this is working in wide, or you can do broadband. Okay, my screen resolution is a bit bad, but this means broadband. There's more features. You can go to advanced options. We don't change this now. You can kind of tailor the meshing by giving some guidance how much you will increase the mesh quality every step. You can also do more kind of complex mathematics for meshing and for field density, but we can actually switch this to mixed order. So that means that every tetrahedron or triangle, you can use more mathematics or less mathematics automatically. So mixed order is typically good to use, and the direct solver is the starting point. You can leave everything as a default, but this is just nice to have active. There's even more features. You can bring the mesh from the other side, and you can save the fields or not to save the fields. Saving the field, electromagnetic field data takes more hard disk space, and if you don't need it, you can switch it off, and so on. But basically, the only thing really you have to do is to say what frequency you are interested of. Oh, this is now the meshing frequency where we create the mesh. I click OK. And then it will ask automatically a sweep. Sweep means what range of frequencies you would like to investigate. So we are meshing this solution with 2 gigahertz, but now we can also think about that. Let's say that I'm interested of 1.5 up to 2.2 gigahertz. So this is the range I'm sweeping my data points, and 401 is too much. I will limit it to 201. So basically, this is just giving us kind of like a spectrum analyzer. It's sweeping a specific frequency band. This is doing the same. So this is equal to spectrum analyzer frequency sweep. So and it's good to do. This interpolation is kind of using just interpolation to find the S parameters. The most accurate is discrete, but it takes more time. It will do all 201 steps. Interpolation is just doing it as long as it can see that the error is good enough and stop automatically. So now we got the solution 1. So I can always change the names here, like my solution 1. Oh, sorry, no spaces here. So solution 1, like this. I can also change the name of this. I can say that this is ground, and the cylinder is my monopole. Like that. So now we have basically all required to do the simulation. So we can do the simulation, but before that, I will add a little bit more mathematics for this. So now we have done this. So I could go here and say that analyze all, but before that, I will do something more. I would like to see more information about the radiation of the antenna. So I will go here and click far field, infinity sphere. This means that I'm willing to capture and measure the radiation highly in detail. So this will create us a ball around this antenna, which is kind of ideally far, far away. And this is capturing the energy, how much energy this antenna is radiating, so that we can measure the energy. So I'm adding far field radiation sphere around the antenna. We can't see it, it's there. Now we got infinity sphere. I can also add near field sphere. I can say once again sphere, and I would say that it's 0.3 meters, 30 centimeters far away, and like this. Now I'm measuring near field data. Okay, in this case, it's maybe close to the far field already because it's 30 centimeters far away with 2 gigahertz. It's actually far field, but I can change it. Maybe let's say that let's take it 0.2 or even smaller, 0.1. Okay, this is maybe too small, 1.5. I don't want to be instead of the change region of the more close you come with the antenna measurements, the radiation measurements, the more complex data you will get, the less useful it will be, because really close to the radiative element, you are in a near field chaotic region, and it's just an approximation, and it's really hard to use any good data for that. So anyway, now I'm measuring the radiation really far away, like ideally 1 kilometers far away or something. It's just measuring the infinity radiation pattern. This is giving us the near field radiation pattern. Well, we don't need this second one. It's typically not interesting, but this is really interesting to do. Once again, I will save the project. So this is all the setups I need to do in order to simulate this kind of simple setup. I was drawing the CAD files, adding my ground reference, radiation, giving the excitation here, and adding my frequency, which is 2 gigahertz, and so on, and sweep. Then I was adding the infinity sphere by just radiation, far field, infinity sphere, add a measurement. Now we can go to simulation step here, simulation sheet here, and we can validate. Is it okay? Now it's saying there's one warning, and we can see that my radiation boundary and my ground plane are on same level. Yes, I know. I was doing that by purpose because I don't care the radiation below the ground metal. There's no radiation really. So warning is okay. This is just a warning that please note. Sometimes these warnings are something to think about. Like warning, there's no good contact between the excitation and the ground. That's fatal error more or less, and you have to fix it. But it's just a warning here. And then I can do analyze. I will click on analyze, and hopefully my VPN connection is is active, so that I will get it will check the licenses at this point, and there's just an error message if the VPN is not active. So I'm using laptop here. So, and my licenses are actually in Sweden. So it will ask the licenses over there. So now we can see that it's starting to do something. I will go, it's automatic. Something happens behind. We can go to solutions and convergence, and we can see steps it will take with the meshing. So now it's already done 4 steps, creating the mesh on for the calculations. This is explaining the S parameter error. So we can see that now it's starting to go down. Hopefully it will go below this target line in order to get, okay, now it's saying convergence, there's a convergence. So we have kind of accurate data. Now it will start to do frequency sweep. And maybe you can hear my laptop is running hot now here, so it's doing the calculations. And you can see that actually the error was only 0.01% about, which is well good enough. 5% is already reasonably good. And here we can see what's ongoing. Okay, it's done, basically. This is a laptop, and it ran in 1 minute and 3 seconds. So, and it was using how much memory? 500 megabytes. Nothing. It's a small design, easy to run, simple. So basically now we have results, but as you can see, nothing comes visible. So we can go to results here and do plot different results here. Like here, terminal and 2D S parameter. It's proposing S11. We have 1 port, 1 excitation, so we can't get S21. We get just S11, which is the reflection coefficient. But that's the most interesting with antennas, because that's saying what's the resonance frequency of my antenna. So everything is as it is. So I'm using my sweep 1 solution. I have only 1 solution, and using the sweep for and X is frequency and Y is this 11. So new report, and that's it. We got a report here, and we can see that actually we got the resonance frequency visible here. It's about 1 point. Oh, we can add a marker here. It seems to be somewhere here. So my antenna is resonating with 2.16 gigahertz, and to be honest, this is not really good antenna. It's only minus 3 dB kind of losses with my signal. So this is not good antenna at all in real life. Typically, you are expecting really good losses with the resonance frequency. So lots of energy is lost and radiated away. But anyway, now we know that this is my resonance frequency. So my antenna is the most efficient about this 2.1 gigahertz. So okay, that was nice to know. That's typically the key information the antenna designers are looking for. And by the way, this my antenna port. If I go to my excitation, it's 50 ohm. So as this is a default. It's a 50 ohm excitation port. I don't know if my antenna is really tuned for 50 ohm. It's maybe not. So I can go also. I can get more results by right click here on the results, and this was the one we just created, rectangular plot. And I can also do the Smith chart to my antenna. So it's not really 50 ohm, we can see immediately. Then we can go, okay, let's do something else before going to more in details. So I'm very interested about how the meshing looks like. So it's not visible. So I will select everything, right click, plot mesh. And it's saying, yeah, here use this my solution data for that. And this is created now automatically by the system. So you can see that there's less rectangles or tetrahedrons around the corners. And there's a good reason for that. There's less happening, but a lot of happens close to my excitation port here. So you can see that my excitation is having high density mesh, and same for the antenna element. And if we look the antenna element, it seems to be only that the surface has the mesh. And why? Because this is a high frequency. We are not interested what happens inside of the solid metal piece, because we know that electromagnetic waves are traveling on the surface because the skin effect. So we are just meshing the surface. If I click active this, you can see solve inside is non-active. We don't need mesh inside of the solid metal pieces and we're simulating 2 gigahertz. So basically this is the mesh, and we can see all these plots we are doing here. If I can activate or deactivate it under here, field overlays. So I switch it off. And this is the plot visibility back. So that's one way. If I need to know a little bit more about my antenna, now I'm interested of the radiation pattern of this antenna. And because we are measuring that with that one, I go to field overlays. Oh, actually, no, results and terminal plot and 3D polar plot. So it's asking, yes, use the S11. And sorry, no, I'm not interested of the polar plot. I need to go to here, fields report and field report and polar plot. Wrong way once again. I have here far fields. There's too many polar plots. So I'm willing to see the antenna radiation far away in 3D because I'm interested of the gain. There's different gain values. So we have the basic gain, system gain, which and realized gain. The difference is that are you willing to include so for example, if you are using excitation circuit to drive the system, you can add matching components in SPICE and excite the system by using them. You can also see is it accepted power or received power of the antenna element. So, but let's use the simple gain and total gain. And by default, I always use DP here. And now it's using the radiation infinity sphere coordinate system to plot something. So I click OK, and this is my radiation. So what it means. So basically, I will actually go click here and should we, okay, let's keep it as it is. I'm not editing it now immediately. So the red means lots of radiation goes to the red direction and less radiation goes to, for example, this direction. And now it's because this is just a plot, it's really hard to see how it really aligns with my antenna. So I can go here and plot fields, radiation field, and I'm choosing my my radiation plot like this. Now we can see one interesting thing, because my ground is not a good conductor. Basically, in theory, we have radiation also below the ground, but I'm not really interested of that. I'm interested on the top side because this is on top of the ground. So this is the energy which is kind of reflected down, because this is not ideal ground. My ground is steel, not a good conductor, kind of. So we can also scale this up. So this means that how this antenna radiates really far away. So actually, I should actually look it like this. So this is just explaining that how much energy I will have different directions, and why it's not radiating on top of the antenna. This is a monopole antenna on ground. So actually, you don't get a lot of signal up from the along the monopole. So it radiates like a donut. But because this is not ideal, you can see reflections from the ground. So why it's not like a donut is that you have a bouncing electromagnetic waves from the steel plate. And that's why you have this kind of uneven radiation around the antenna. So I will hide that. I will deactivate my plot. We can also see something interesting by looking at the E and H fields around the antenna. So you can do it by having planes. So this is coming anytime you have a coordinate system, you have planes X, Y, Z like this. And these are something easy to use for plotting cut planes. So I will select this plane, right click, plot fields, E fields. So electromagnetic fields and magnitude. And I'm choosing the frequency 2 gigahertz, yes. And phase 0, yes, that's okay. Just default and okay. Okay, looks nothing. I need to change the scale maybe to logarithm. So I was double clicking this color scale. I just changed the colors now, and I say that use logarithm scale. Now we can see much more. It's just for humans, this is much more convenient. Okay. So now we can see that there's a strong electromagnetic fields around the tip of the antenna here. And if we go up here, we can see that it's with this phase 0. You can see this is a phase, because this is a sine wave, the excitation is using a sine signal. So we can see it's kind of, we have a 0 null here, and we have a kind of a high field density on top of that. And now we can start to see something happening here. It's actually the radiation of the antenna, electromagnetic waves, but it's not visible really well. We can tune up the color scale to make it even more visible. Maybe I'm just testing. I don't know exactly what's a good level here. Maybe I can switch that. Oh, 1. Okay, now this is maybe, it's not ideal, but it's more visible for human. I will even, yeah, I'll just magnify the colors by changing the scale. And I'm having just 33 levels, because what I'm interested, I would like to see these borders here, just make it nicely visible. And I can also do some animation for that, because we are plotting this now with 0 phase. We can have different phase shifts along this. So now we can see how it behaves over the full sine wave, kind of over the one round of the phase. So it's going from 0 to 180 degrees and back. So this is how my antenna radiates. And this is kind of a 2D seed presentation of that. So we can see that kind of the electromagnetic wave travels along the antenna, and because this is not really tuned for this frequency, we can see that this is not really good antenna, because this is not symmetrical. For example, this my E field density here. So it's not radiating in a really good way. We should kind of fine tune this antenna now based on this simulation result. I can also export my export this as a video file or something and give it to the PowerPoint. That I can also choose my face by moving the window and so on. There's many other ways to solve the E fields. I can choose a vector representation for that. Plot fields, E fields, vector. And the same, and already done. Okay, it looks awful, and it's just a scaling once again. The computer has no information how it should look like, so I will just adjust. So maybe something like this, and I could maybe add more arrows here to make it more visual, like this. And so I can play with these numbers so that I will get a different visualization for my field plot. Okay, so take that off. One more, typically what you can see people, or especially antenna and EMC guys, to do with this kind of simulations is to show the radiation by a slightly different way, far fields and radiation pattern. I once again take the same gain, total gain, and I will say new report. Oh, okay, I need to change that to phi. So this is my antenna radiation, but now it's, as you can see, it's also showing us to all the phase values. So this is not really useful by this way. So I need to maybe limit. I'm interested of some specific phase values. Now, typically it's 90 degrees. Okay, not 90. In this case, I need to take 180 maybe. Oh, sorry, I was choosing wrong one. Here. No, phi, yes. So I will take specific value, maybe 180. Is it opposite way? I need to take the something which is different, 45 maybe, or something like that. Yeah. Like this. And one way to modify that is, actually I like better, they're just slightly different. I will change the coordinate system this way, and let's redo that gain plot using theta. Use all, apply. Yeah, this is more easier to us, and DP unit, by the way. Now it looks the same as before, but now we have all the phases once again. So I will just choose specific values to my. Oh, okay. This is having, but this is having all the phases now. But it looks pretty stable because this is ideal antenna, round antenna in infinity-sized ground plane. So we can see the kind of the magnitude from this radiation pattern, in which direction the antenna radiates. If you're interested, what's the system gain? If I apply, it's just plotting the the same information. Oh, sorry, that's not the DP. It's more or less the same data because we don't have difference really in this simple setup between different gain values or realized gain. Sorry, DP once again. So all these gains are giving more or less the same value. They can be small difference between the incident or accepted power and so on, but basically we can play with the basic gain here. You can also, if you have a circular or polarized antenna, you can plot left hand, right hand gain in different coordinate system and so on. So depending what kind of data you are looking for. You can also specify mathematical operations, do math for the measurements. So basically, there's a full mathematics behind how to do these calculations. It's not limited what you have here. You can basically get the raw data and do your own math based on the results. And as you can see, you can also plot in different scales. That's when required. There's more plots types. You can also go to 3D spherical plot and gain once again. Now you can get the different planets or okay, this may be nice. Just don't use a DP scale. Just use a linear scale. So this is giving you the same radiation, but now just plotting it kind of on top of a sphere. If we are interested how it looks between the far field and near field, I can go to near field plot and 3D polar plot. And now we are not having gain, we have the E field density data. And it looks most likely pretty different. We are now in near field, which is more chaotic. So it's not, or should not be, let's say, as smooth and nice as we have the far field really far away. Yeah. So you can see that it's more difficult to understand how the antenna, so don't look at the bottom side, it's kind of the underground, and these are kind of just almost, we can say, artifacts, which are because of the mathematics. But this is a near field, and this is kind of approximation always in the near field. It's more chaotic field density distribution. This looks actually pretty nice, to be honest, for near field plot, and this is the linear scale for that. So you can see huge variation. That's why we use a DP scale typically with this. We can use the pointing vectors. We need DB, of course, in this case. And so on. So when we had these both spheres here, near field and far field, we are, after that we are able to plot all this data. And we also can go to here to far field and compute antenna parameters. So if you are sometimes going to do antenna design or tuning, this is the place to find a lot of detail data, how your antenna behaves, directivity, peak gain, realized gain, system gain, accepted power, and radiated power. Now, that's my antenna is bad, really, based on these numbers. So we should have different dimension for the antenna with 2.1 gigahertz. Oh, this was 2 gigahertz actually, not 2.1. So this data was not with the perfect frequency. So that's basically how to do the reporting. So and the result. So you can also find the buttons here. I was just using this menu here under the results and the field field overlays. So here we can have the create the reports here under the field. So I was not using anything else except this my single XDS and single monopole antenna, and so on. I can, and the beauty with simulations is the sweep. We can sweep different. So if I want to tune up my antenna, now it was a rigid antenna with a fixed size, but now I can change this height value as a parameter, height. And I say that, yeah, 0.1 meter, it looks the same, but now it's, if I click you can see it's a parameter under here, and it's a variable. And now I can actually play much more with this one. I can go to my solution setup, for example, and say that I'm using this height value for extra calculations, derivates. Derivate means that it will, and I will restore the design. That means that now I'm actually a little bit play with the height variable, even I'm not recalculating all the different height values. So it's kind of approximating if the length of my own monopole antenna will change, it will approximate how it will change results. So it will recalculate my setup in order to get the derivate data for that. It should look more or less the same as before, but now we can see a little bit more with hopefully with the S parameters if I change the size of the antenna. Oh, by the way, if you have any questions, we have the raise the hand features with this or the chat. So we can use the chat, for example, to send. If you have any questions, just stop me and ask. So this is no one-way information I'm sharing. So if you have any questions, please be free to send a question or raise the hand. This is now doing the adaptive passing. Step 4, step 5. And step 6, now it should get the convergence done, yes. And now it will do this frequency sweep and doing the field. Oh, basically, the more calculations you set up for your simulation, the more time it will take. So if I add a far field, near field, or some other mathematics, yeah, it will need a little bit time to do that math when doing the solving. And most likely this is using now 8 cores. It's using 90% of my 32 gigabytes in maximum if there's. And here we can also see the mesh statistics, how many mesh elements I have. This is really easy simulation, only 20,000 tetrahedrons inside. So that's why it runs pretty fast. Now it's done. Okay, now I can go to, I was saying that I set up the derivate for my monopole antenna length. I go to tools, and now I try to recall the location. No, sorry, it was under the HFSS and tune reports. I will also open the S parameter file. The results, that was the first one we did. Now it's the nominal value. Now if I change the antenna size, hopefully something happens. Ah, okay, I need to update update this. I need to, this S parameter file was not using my, derivative. I need to use the height for that, apply. Okay. Go back, because I did that before the tune reports. Now, if I change the antenna smaller, let's see, is it going to affect my antenna parameters? Is this millimeters, by the way? Now I need to, I'm not sure if this is, I don't know, the size of the antenna. I need to double check the, let's go here, back. Did I change it? It was not activated. Now it should be activated. No, it's still off. Okay, I will do just to be sure that it takes the all and yeah, tune. Sorry, that was missing. I had to choose the tune S parameter in order to make it active. Now it's including the derivative information. So what antenna designers really do is they are kind of changing this, and now you can see that the S parameter is changing. If I do my antenna smaller, you can see that it seems to go deeper, but now I'm even not able to see it. It's in too high frequency, so I need to increase the size of my antenna even a little bit more, like this. So if I add some length to my antenna, it will resonate with 2 gigahertz, which is pretty good. So apply. And now we got something like a 5. Oh, what's the? It's still not resonating really well, but it's a little bit better than before. 3.98 dB radiation. So this is what the guys will do with simulations. They will use the simulation to fine tune your design. So if I go to my antenna now and see that my antenna is actually, it's 1 centimeter, almost 1 centimeter longer than before. And now it resonates with 2 gigahertz, much better. And if I go to E-field plot like this, and I will choose the 2 gigahertz. And do I have the antenna activated? Oh, okay. It seems to be that I lost the results for some reason. I did. Oh, okay. Because I changed it. Yeah, because I changed the size of the antenna. So this is now 1.10, almost 11 centimeters. I of course I need to recalculate. This cross means that there's no data because I changed the size of my design. It's this chart kind of deleted my existing results because now I need to kind of recalculate these values in order to get the data. So you can see it's empty now. So now I need to go here and resolve that with my new design to get it kind of visible, all the results once again. But yeah, basically the idea of that is that if you have a parameter, you can parameterize anything more or less. So and you can also do even more complex sweep. So you can add parametric sweep. I can sweep here without the derivatives, the size, and I can also do sensitivity analysis. So I can say that I can tune my S parameter, and I can choose, for example, okay, I have only one here. So this is the one I'm using for my sensitivity analysis include. So basically, now if I have more, let's say if I have 5 parameters, now I can run a simulation setup where the system is automatically testing all the 5 parameters and saying which one is giving me the highest change to antenna performance according to my kind of target or settings. So you don't have to do all the manual work to optimize your antenna. The system, you can do that with the system by using advanced analysis like optimization tools. And there's even design of experiments or statistical analysis and so on. Of course, this takes time. So if you have 5 parameters and everyone has 5 options for the height or width or impedance or whatever, it needs to run all of them through, or in design of experiments, it will just run kind of systematically enough different variations to be able to see the optimal solution for you. So this is a design tool, optimization tool you can play with. But more or less, this is kind of a typical workload you will do with simple design. On top of that, we can also do a little bit more kind of complex scenarios. This is still a simple case, but just a simple demo. Here we have a circuit board with a trace and a small antenna with the stop. And then we have something else. We have hide the grid, and I will hide the radiation boundary. Here we have a conductor and a metal plate. And this is actually one of the qualification tests, which is the IC ESD testing or EMC immunity testing. So we are giving, there's a port here, zooming in. So it's shooting high current pulse to this metal plate. This metal plate is radiating energy. Like hopefully I have something to like this. So this is shooting electromagnetic waves around. Let's make an animation here. Oh, sorry, this is not correct animation. This was something else. Okay, don't waste too much time on that. But this is how the field is propagating. I will deactivate something away. Maybe that's not so visible either. This is the combination of the fields, what's ongoing here. Magnitude. Oh, maybe that's more interesting. This is how much energy will couple on this this component here. That's basically what we are interested of. How much voltage current will see my circuit board? How much energy we can see with the two? So we have 50 ohm termination on both sides, and you can see that a lot of energy is coupling to the antenna because it's in a kind of 90 degrees. So it's kind of receiving antenna for any field which is radiated by the metal plate. And it will couple on my circuit board and cause some immunity emission or immunity issues with my IC in the worst case. So I have 2 options. I can seal the antenna with metal or EMC sealing, or I can have filters here to block the signal to couple inside. This is more complicated access scenario than this is a time domain and frequency domain combination. So basically what I'm doing, I have a circuit SPICE, which is, and I have a dynamic link from my frequency domain into time domain, and I'm shooting a wave inside. This is my source circuit, and it's pushing this kind of time domain curve inside of my into my radiation plate, and then I just go here and push excitations data back to the 3D, and then I can go and plot the magnitude in time domain in this setup. So I'm using the SPICE circuit to excite this with specific matching components, and then I measure here the voltage, let's say. Okay, I don't have no data here visible because I haven't done the calculation for that. But yeah, basically this is kind of more complex. You can also see lots of good examples. If you don't know how to do this kind of setups, just go to File, Open Examples, and here under HFSS, you can see different kind of, let's take antennas. So we have more complex structures like array antenna setup. So this is a modern technology nowadays. This is how antennas look like. They are made of, or let's say the array antennas look like. They look like single small elements you excite one by one, and then you're able to kind of excite one or several of these cells and see the kind of the outcome of the system. There's also some easy ways to do your own antenna design. There's a toolkit inside. It's under the View ACT extensions. Hopefully it comes visible. Yeah, slowly. Yeah, allow access. Launch switch arts. Antenna toolkit. There's switch out for 5G antennas too. So we can build up nice, let's do something which looks nice. Look, the horn helix. This is always nice. Yeah. So I can say that I want to have this 20 gigahertz and synthesize and finish. So I'm willing to have a helix antenna which is running with 20 gigahertz, and then the system will design it for you. Okay, it's not ideal. It's giving the best guess based on the analytical equations we can get for that. Why these kind of antennas are interesting? Think about airplanes, or especially satellites, which are moving, rotating. This kind of antenna has kind of round face, so it doesn't really depend on which rotation shape the polarization is kind of rotating, so you will always get the same signal amplitude whatever rotation phase this antenna is on the satellite. Satellites are typically rotating slowly, so this antenna is immune to rotation because it's kind of rotating by itself. So it will create an electromagnetic wave which is easy to receive with any polarization. So basically, this is already something we can go here, simulate and run the simulation. So everything is done for you. And this is easier. You can see there's now 4 excitations because we have 4 kind of antenna elements. And it's also giving you all the reports. Okay, it takes maybe 10-15 minutes to run this simulation, so I'm not switching that on. But basically, these with charts are easy, and you can always go and edit that after that, or you can copy paste. Just go select everything, Control-C, copy, and you can copy that to your own design and plug in play with that. So an efficient way to kind of build up your own antennas. Not only antennas, but there's also so for the Maxwell, and this you can download this with charts from the Ansys webpage. There's more. I'm just playing with the higher frequency, so we have just these few visible here. So this is kind of snapshot of the software. So you can, as you can see, you can have multiple projects on top of each other. You can also, when you have the results, you can go here and copy the data and paste the data. So you can switch between the reports and kind of tune the reporting a lot. Oh, time is running. It's already 1.5 hours we have spent. Please let me know if you want to that we are quitting in after 10 minutes, or is it possible to expand it until still half an hour? It's up to you. Which way you prefer?
I think Pasi, you can go as ahead as your best. I don't see any opinion in the chat or.
Okay.
So up to
So
you.
yeah, maybe if we can do it so that I will continue until my time on 1 o'clock, so it's 12. But if people need to leave, just please be free.
Yep.
So yeah.
Thank you.
Okay. So at this point, I will switch the software, and let's speak about the circuit board simulations. This is kind of, let's say, if I'm looking what the industry is doing, almost maybe 50-60% of the simulations are with the circuit boards, and the rest 30 to 40-50% are with 3D structures, and many times they combine these together. So this is my circuit board. This is downloaded from the ODP++ file, and it's kind of a multi-layer circuit board. I will switch on all the layers active. So this is just the expansion, so you can see there's multiple layers. Make it smaller. I switch off some of the colors to make it more visible. And typically with the circuit board, we are looking from top to down. Now I have all the layers active. I can activate just the top layer or all the layers at the same time. So we can see traces. So what we can do with the circuit boards, with this is the SR wave. Basically, we can simulate now a lot of different features. We can simulate how the current is spreading on top of the circuit boards. We can calculate electromigration, SYZ parameters, resonances. We can do frequency sweep analysis. We can also capture the far field for EMC purposes or near field. We can also see that if there's emissions, what's the immunity of the circuit board. But this is the key area, let's say, for most people, is to do circuit board signal net analysis, impedance scans, crosstalk scans, eye diagram scans, and timing analysis for the signal nets. So let's do really something simple at first. Let's see that I have okay, this is not high-speed circuit board, to be honest. This is just a demo circuit board. Don't expect to see this simple circuit boards in real life. I will go to view and top, and view and unselect. I will just choose show all. Yeah, I will just look at my settings like that and select the net. So let's do some simple. So maybe this is my net. As you can see, it's kind of a simple trace going on from this node net to this IC pin. I will do it now kind of manual way. There's automation for that, but now I will add a port from this point to, where's my ground? Hopefully this. Yes. So, okay, it was a power net. So I'm not choosing that one. It's a power signal. Let's do some alpha. So maybe this is a clock. Yeah, clock signal. That's always nice. Clock signal is always interesting from signal quality point of view, but except now there's a problem. This is not really good. You can see this clock signal goes to several components. So I would like to have a single trace, which is easy to understand what we are doing. Ground. Okay, this is, so maybe this next one. Yeah. I will unselect everything and take, this is maybe, this is a bit longer. Yeah, okay, this one. Actually, I have no idea what this signal is, but I don't care. Now this is the demo, so I will click a port here, and is this ground? Yes. So this unknown net to ground. There's a one port, 50 ohms, yes. And I add the second port on the other side. Okay, once again. Where's my ground? Maybe here? No. I should find a ground reference somewhere. Once again. Where is my ground? Maybe here. Okay, that's ground. So the length is not important. This is kind of ideal excitation to this single small net in here. So now I go to simulation setup. Now you can see many of these buttons came active, and because I have set something I can use for simulation. So I'm having two ports. So just do the simple simulation from 50 megahertz to 1 gigahertz. Number of points 100. And 101 data points. Why 101? When you plot something, you will get value to both to 5 megahertz and 1 gigahertz, and then 99 data points between. This is just convenient. And launch. Okay, yeah, let's replace the existing. So now it's doing the simulation. So basically, this is the method of moments solver 2.5D. We are approximating every single, so it's doing the meshing for that, for the circuit board, but it's kind of expecting that you have FR4 dielectric copper layer, FR4 copper layer. So it can use kind of RLC simplification for the traces and ground power planes between. And this is much, much faster to do these simulations than in full 3D, where we are also expecting that we have radiation boundary around and we're meshing the surface, the volume. Here we are meshing only the surfaces of the circuit board. So that's it. It's done, and I can go to results. Now I have one button active. I have the S parameter file. All right, so, okay, it seems to be that I had actually some other ports in my, this is old design, so this maybe I have played with this many times. So now we can see a couple, two plots at the same time. But this is the one I was simulating. I was not interested of that. This is the one we were simulating. And this is now S21, if I can see correctly. Yes. So this is the, and that's why we can see small losses. So it's pretty good signal net. So really less than 1 dB attenuation. And there's really hardly no attenuation in low frequency. Only here around 1 gigahertz, we get some more attenuation. This trace is most likely not high frequency trace anyway, but yeah, we can also see the S11, and this means that most of the energy is lost, which is good because this is 1.2 one termination to 150 ohm termination, and so most of the energy is lost by the termination and not radiated away. So we have a good attenuation, which is as it should be. So basically, this is one way to do the high frequency simulations. But the same software package, we can do also many other things. For example, we can do power simulations. So I will go here. I will take current source is here. Now I should find a place to put my, sorry, I don't know this circuit board. So this is that's why always the circuit board designers will do this kind of simulations. So I will guess, hopefully this is power net. And now I need a ground. This looks like a ground, let's see. Okay, yes. So P28 volt and okay, VCC bad, not good. So I will. Oh, okay, there's something old. I haven't done this once, but this looks good. So let's use those. What are these ports, by the way? Select, click. What's that one? It's 28 volt source. Okay, let's use that one. Okay, I go to simulation, power ice. Okay, there seems to be lots of ports already set up. I will just say that, yeah, let's change this to positive to ground. Oh, there's a lot of this. Oh, let's see, it can be a bit complex, but we can see about like this and launch. So basically what these are, they are power voltage sources here. Now it's doing the calculation. And typically this takes minutes or something. So, and because the simplification of the CAD geometry as a circuit board, we don't need to do full 3D and we can speed up calculations a lot. Why they are doing this? Okay, easy to understand. S-parameter extraction of the circuit board, and you can kind of get the S-parameter file and put it in SPICE and do SPICE simulations. For this power, we are typically interested where the current goes. How much current goes? Is it heating up? Is it maybe this this red power grid is too narrow and it's heating up, or maybe some specific vias are heating up too much, and we are kind of burning the via, and the circuit board will fail. So now we should have a DC IR map. Yes, but currents and voltages. All right. And this is the magic. Now we can see how electricity is moving and how much electricity is moving. So these arrows are pointing up where the current goes. And for example, here we can see that these two vias are kind of draining a lot of current because these are most of the power supply vias, and that's, we can also see that those are pretty heavy, so lots of current goes that. We can see that here nothing really happens, so the current has always a loop. Current will travel back, it will go through. Okay, I can hide. Now there's too much information at the same time. This is the power distribution. We can see that this area is having the highest power density in this case, and especially these two vias are kind of, this is the hotspot, by the way. This is the where it will heat up the most. So for example, this IC here, you can see that this corner is more yellow and this is more green. Okay, maybe not a huge difference, but if you're willing to expect that the circuit board will survive 20-30 years in use, most likely these pins are going to fail before these pins are failing because of mechanical stress of cooling down, heating up, cooling down during the time, and so on. And this is the voltage distribution. Oh, this looks nice. So we have a good distribution of the voltage. So this is not a problem on this circuit board, but this looks a bit more interesting. This is now only showing the surface current density. So once again, we can see that a lot of things happens on these 2 years. Now it's the question how much these components can survive, how much these vias can survive current. And this is the reason why we have a wide power, not a trace but plane, splitting the power to wider area, so it's not heating up too much, and so on. Here we can see it's feeding these components. Oh, sorry, this is the source. So this is the source of the current, and it's spreading here, sunk away by these components. Yeah, and this is the current density, and okay, the current via current is here, and most likely we can see. Can we see the via current? Okay, no temperature plots. Okay, I'm looking for via current. Oh, okay, sorry. Yeah, it is. But this blue color means it's still reasonable. I'm looking for red vias, but I can't see any really problems here with this one. Okay, but that's more or less the basic things, and then we can go and get something more and plot iceberg power map. Oh, yes, I didn't activate that in my simulation. So, okay, we should run it once again by activating the yes plotted power map. I was not doing that in my simulation setup. Of course, I could do it. It's pretty fast to do. So I forgot to click disactive. So relaunch. Yes, hopefully it goes fast. So basic idea is that by having this power distribution data, we can launch. Here we have a button of iceberg. So this iceberg will also now, then we can plug in coolers. We can have fins on top of the IC packages, and then we can run with specific airflow, with specific air direction, and we can see how it will cool down based on the heat, the cooling system. So, and it's including both the IC power sources and the traces and circuit board heating. So it's a combination of power component consumption and the circuit board resistance, resistive heating. So it's really accurate. So we can predict the circuit board temperatures in, let's say, ±2 degrees, even ±1 degree accuracy, at least in most cases. Of course, if it's really complex, lots of high components, uneven power distribution inside of the component, the results are not ideal, but close enough many times. Okay, so results, DC power map. Now it's doing the calculation for that. And I forgot to mention, there's a EMI scanner here. This EMI scanner is really efficient. You have maybe 200 parameters to set up, but it will investigate EMC problems from your design, and it's automated. It's doing heavy job for people. So this is my power distribution, power kind of map, which is something we can feed into iceberg, and iceberg will then calculate the temperature. So I would be a little bit concerned of these two components, because these are kind of pinpointing hot red. No, okay, not temperature, but power. Okay, this is of course a fake simulation here, so we should not look. But if this would be a real simulation, there might be some heating problems with these two components and these two vias if it's limited by the width of for the current. But otherwise, this circuit board looks pretty nice and evenly heating up. So these two main components seems to be more cool than these two, but maybe the difference is not so huge. And typically the main challenge is high gradient. So if you have really rapid change with the temperature, it means that it will stress that specific area and solder joints can fail. We might have some other specific vias here because we have these sources here. So we have some specific vias here also with yellow, red color. So it means that lots of current will go through. Yeah, time is flying. It's almost 12 for you, 1 o'clock for me. So this was an overview of few of the features we can have with different simulation tools. We have full 3D, we have circuit board simulations. I can go here and open examples and do some Maxwell low frequency simulations like this is a coil. This is a metal coil and we can put current through and see how this heats up, how much power is kind of consumed by this kind of winding. And we can also see the magnetic fields and behaviors for that. So we can do whatever you measure, we can nowadays simulate with electromagnetic simulation tools, and we can do even more than measurements because we have access. For example, we can go inside of this winding and measure the power distribution inside of the wire. That's almost impossible to do by measurements, but with simulations, we have access on any point in the design space. So that's one of the key reasons people are using simulations to design, optimize, analyze electronics. Time is flying, so I'm happy to receive any questions, but it's also possible that if you have any questions, you can collect them and send it to me as an email or something like that. So happy to keep feedback and information if and when required. I just hope that the people and students are willing to try and learn to use the simulation tools.
Well, thank you very much, Pasi. It has been very instructive, also very, very powerful tool. I was just wondering if we have 1 minute for one question or
yes,
any comment.
I'm happy. Yes, please.
Yeah. There's any questions? Not really. It seems everybody is ready for lunch.
Yes, I think so. Same for me. So
yeah, thank you very much. It's been very helpful. So we're going to upload the video. And also, for people who are interested, probably going to post a small project using Ansys. So we'll contact you later, Pasi.
okay.
Yeah.
So I hope you nice lunch and a nice weekend coming up. So let's be in touch. Thank you.
Thank you. It's been a pleasure. Bye bye, everybody.
Bye bye.